Yes.
Ok, donc, oui, j'ai compris.
Okay.
So, thank you, Denis.
Ok, donc je peux acheter en français, français peut-être. Non, Federico, you prefer speak English. I try English, okay, and I switch if I need words that I don't. Okay. So this is a talk. Thank you very much, Paul, for this invitation. Yes, it's very kind invitation. So this, I'm not sure you can see. Yes, I have to change the light maybe. Okay. So this is a talk about a few results concerning the comparison of stationary processes. So this is finally a joint works with different persons that I present now. So this is what I want to present is a continuity of some works with Paul, with Eva, with Laurence, and with Anne-Françoise. Okay. The motivation of the talk and of the work is if I show you 4 trajectories of strictly stationary processes, it's not easy to compare with such processes. Okay, it's difficult to say they have the same structure or not, and you can try to answer if they are the same or not, and if I give you the solution. Actually, the 2 first processes are Arfima with parameters 0.3, and the last processes are also Arfima but with other parameters. So the main purpose of this talk is to propose a method to compare such processes. First, to compare 2 by 2 strictly stationary processes. So this is these are works that I made with Laurence, and with Paul, and Françoise, and Eva. And actually, I will show you also an extension of such comparison of processes that make possible to compare simultaneously K processes, for instance. Okay, and finally, so this is the story. So finally, we will see that we can use such method of comparison to construct a clustering method to make a clustering of time series, for instance. A brief history. First, when you want to compare a distribution of, say, IID observations, and you want to compare to a given distribution, you have many possibilities to construct tests, such a test of goodness of the test. And one possibility is to use what is called the smooth test that was extended by Ledvina in 1994. And this is such approach that I will show you in a few minutes. Okay, so this is the starting point of the comparison with smooth test. Then a few years later, Ledvina and another co-author, they proposed now the comparison of 2 IID samples. Okay, and we extended this result concerning two distributions. In the case of X and Y are 2 samples that can be paired, so you can observe the 2 populations but with dependence. And in 2009, Monk and others proposed such a technique adapted to alpha mixing processes. So they use smooth test to compare the marginal distribution of process to a given distribution. With Paul, in 15, we extended the work of Monk and we proposed a smooth test, again, ST for smooth test, to compare the marginal distribution of 2 processes with short-range dependence. Okay? And extended, we generalize this result to the case of strictly stationary processes with long-range dependence. And finally, with Laurence and Françoise, we extended again this result in the sense that we not only compare the marginal distribution, but the whole distribution of the processes to say yes or no, they are the same. So in this talk, I would like to show you how to construct such a kind of test, and to show you how to extend this two processes approach to the marginal approach to the whole distribution, and finally how to extend all these results to the case of K processes. Okay, so we do not only want to compare two processes, but K processes. And finally, I will give you, if I have time, a way to extend to the nuclear case. And also here I will include a clustering method that can be used to, if you have K processes, then to make clusters with similar processes. So this is the plan of the talk. I introduce this test for just the margin. Then I show you. Huh? I don't know. You want j'enlève ça du coup?
Non, je sais pas, mais j'entends rien.
Mais t'as mis le son?
Non, j'entends rien. Moi, j'ai pas mis le son parce que je pensais que toi, tu l'avais.
Et là, si je parle, là, tu l'as là?
C'est là, depuis un quart d'heure, tu parles et personne ne t'entend.
Attends. Voilà. Tu coupes ton son et tu utilises le bien.
OK. Là, c'est bon, là. So this
Coupe le son de ton ordinateur.
J'ai coupé le son de l'ordinateur. Je l'ai enlevé. Il est à 0 là. 0.
Non, en entrée et en sortie.
Je sais pas comment on coupe l'entrée.
Écoute, je sais pas. Si tu veux utiliser toi ton son, il n'y a pas de problème, mais il faut faire un truc, quoi. On ne peut pas faire ça.
C'est quoi le problème?
Il faut que tu coupes ton micro.
Je sais pas comment on fait pour couper le micro.
Try in the Zoom application.
OK.
Si tu veux pas utiliser, si tu veux utiliser ton Zoom, ton son, tu le fais, mais tu le fais, quoi, parce que là, on n'entend rien du tout.
On entendait tout à l'heure ce qui s'est passé.
Tu rentres.
T'entendais quand, Laurence? Au début, t'as entendu?
Elle n'entend rien, je
Oui,
pense.
oui, sur le début, j'entendais bien.
Elle entend?
Si, si.
Elle entendait au début, ouais.
Ah oui, moi j'entends. Elle a dit.
J'entendais très bien. Par contre,
Alors reprends. Moi je sais plus là. Franchement, je deviens fou.
Du coup, là, Laurence, tu m'entends là?
là,
Tu m'entends, toi,
très bien.
Laurence?
Là. Oui, oui.
Non, mais donc du coup, je remets mon son.
Laurence, tu m'entends là?
Est-ce que toi, tu as coupé ton son ou pas?
Non, maintenant j'ai remis là, parce que j'ai enlevé ça.
D'accord.
Laurence, tu m'entends, toi?
Oui, je t'entends. Je t'entends.
Sinon, je
apparemment,
coupe
vous
mon
pas.
audio et je branche ça. Ça vous va? Et là, du coup, tu m'entends, Laurence, toi là? Non plus.
Bon, Laurence, est-ce que tu entends quelque chose maintenant? C'est pas possible.
Ah si, elle est son pouce, donc c'est qu'elle entend.
Ah bon?
Ouais. Donc je peux continuer comme ça ou pas?
D'accord, ok. Bah, écoute, oui, je sais pas, je comprends pas ce qu'on fait là. Franchement, je comprends pas. Là, tu vois, il n'y a plus le truc. C'est lui qui a dû faire un truc bizarre.
Je continue?
Ouais, vas-y, vas-y.
Okay, so this is the plan of the talk. I start now with the first problem of I want to compare two marginals. Okay, so of course, the problem is that you can have two arfima with the same marginal distribution, but not the same rule distribution, actually. Okay, so if you say if you say okay, these two arfima have the same marginal distribution, it doesn't mind that they have the same rule distribution. Okay. So we start. I want to show you how to compare the rule, the complete distribution of two stationary processes. First, I start with the comparison. So I say the wrong way. Okay, it's the wrong way that I change, and I start with the comparison of two margins. Because when you know how to compare two margins with smoothness, you can extend to the rule distribution. That's why I start with the bad hypothesis, but I will generalize it after. Okay, so this is the history that I explained. The idea of the smooth test is very simple. Finally, if I start with the comparison of two margins, I want to compare the density of an element of the process CX1 to the density of the margin of the second process, C1. So the null hypothesis is here if you compare the density. And to compare such density, we use an extension in an orthogonal basis. That's the idea of the smooth test. So you have a condition that you have.
Qu'est-ce que tu partages? Excuse-moi. Là, je ne vois pas la même chose sur l'écran.
Comment ça?
Ça qui vous êtes en train de partager, donc c'est justement le zoom que vous avez vu. Non,
je ne vois pas ça.
Vous êtes en train de partager votre écran pourtant.
Départage et repartage,
ouais.
Si tu veux bien.
Partager.
Tu parles.
C'est bon.
Ah, c'est bon, voilà. C'est facile, hein, avec des gens qui sont bons techniquement, ça se passe bien toujours.
The idea of the smooth test is to use an expansion projection in an orthogonal basis. And finally, if you have, you see that the null hypothesis is equivalent to this equality, that is the equality of such quantities, the parameters AK and DK. Then we change the hypothesis S0 and we transform it in a kind of parametric hypothesis, but with an infinite number of equality. And this is these coefficients, which are the projections, the coefficients associated to the projection of the densities, that we want to compare. We can estimate such coefficients empirically. So I show you the form of these estimators. So we assume here that we have n observations of the process. It means that, okay, we could have nx observation of x and ny observations of y. It's just a little bit different. But to simplify, I choose the same number of observations. And anyway, the two processes could be paired, and in such case, you will have the same number of observations. Okay. T'as fait un truc là. So what is the way to estimate the quantities A and B? This is the form of these estimations. Okay. So this is an empirical estimator with a rate that depends of the dependence of your processes. In the case of short range dependence, you have the classical rate, that is the square of n. And in the case of long range dependence, you have here the dependence parameter that is taken into account. And we consider in such case linear processes having this form.
Sorry, here the delta is fixed.
Yes, delta is fixed. It depends of the dependence of your process.
Okay.
We choose the case that delta is less than 0.5. If delta is negative, finally you are in a short dependence case. Okay. So this is for the long range dependence. You have and you have such a rate of the coefficients here with the innovation.
So you need first to estimate delta.
You can, of course, yes, you need to estimate delta. Yes. You also need another parameter that is called the power rank of your process. But here we assume that the power rank is equal to 1. Else you have the power rank that is something like that.
Power rank is the analog of Hermite rank.
Yes. Yes. In the Gaussian case, it's Hermite rank. If we use Hermite polynomials. So the idea is to compare such coefficients. You remember that the null hypothesis is you have the equality between all coefficients. So we start with the first coefficients, and we say, okay, the first statistic is the difference between the first coefficients, like the difference between the means of the two processes.
Et la même chose, c'est que non, ça défile pas, hein, tes slides. Je ne comprends pas ce que tu fais, mais franchement, il y a un truc.
Il faut que je fasse partager globalement, c'est ça? Et là?
Ouais, c'est bon. Ouais. Pourquoi tu fais pas ça?
Je vois.
Moi, je ne vois plus rien.
Ok.
Donc, vous avez vu ça ou pas? Ça, vous l'avez vu avant?
Non.
Non plus?
Dès que tu changes. Ah,
oh,
si,
bah non, mais...
non, ça marche.
Si, c'est bon, c'est bon.
Simplement, c'est qu'il n'a jamais utilisé Zoom.
Non, c'est juste que je ne suis pas très prêteur et j'ai toujours peur qu'on copie sur moi. Donc bon, OK. So the first statistic is based on the first difference, okay, the first coefficient. The second statistic is not only the second coefficient, but the first plus the second. Okay, so it's like if you compare the mean and the variances of the two processes. Why we keep the first one also is to have a series of embedded statistics. That's very important because in such case, this is like a Schwarz criteria or IKT criteria. You have embedded, you have a number of components that is increasing, and you use the penalties rule. Sorry, that is, you mean the highest statistics. You want to detect the larger difference between your coefficients. But of course, this is increasing. So you have a penalization depending on the number of coefficients and of the rate of, depending on the number of observations of the processes. And finally, your statistic is called data-driven because you say, okay, I use this rule, okay, and you can have k that tends to infinity, okay, not too fast, but you have a rule to get that. Then we choose this automatic statistic. It means that when we detect a strong difference, maybe this second one, okay, this statistic will be chosen. But this difference must be greater than k, must be greater than the logarithm of the number of observations. Why? Because it could be noise, and asymptotically, you want to be sure that under the null, this is noise, and then the first statistics is detected. But if really you have a difference somewhere, you want to detect it, okay? And the rate of divergence will be greater than the log of n. This is the power of n. This is greater than the log. So finally, the result, the important result is that, okay, okay, voilà. If you let you let the number of coefficients not faster than the logarithm of the number of observations. Then, under the null, all is noise, and finally, this is the first statistic that is chosen. And here's automatic data-driven statistics will tend to this one distribution. And if you are not under the null, then you will detect the difference, and asymptotically, your statistic will tend to infinity. So this is the basic property of smooth test, and it works very well because you have an automatic detection of the difference between your coefficients, and it gives you a very simple asymptotic distribution. So that was for two processes, and now the idea is to extend this result to no, first, excuse me. First, I would like to just extend it. Yes, of course, yes. This is for the margin, excuse me, this is for two processes, but just to compare the marginal distributions, the density of X and the density of Y. Now, what we want to do is to detect if so I make a joke for Paul. Okay, because this is the middle of the talk. So usually there is an entr'acte. I don't know how to say an entr'acte. This is an entr'acte. So if you just look at the marginal distribution, the form of your process, you can see that they are the same marginal distribution. But if you look at the whole distribution, of course, this is not the same. Paul, tu apprécies. Then now we want to tackle the true problem that is testing the laws of the processes, not only the marginals. So what we can do, we want now to test if for all D, okay, the D joint distribution is the same. So the idea is to use a two-step procedure. For each D, we return the best number of coefficients by a penalties rule as done before, okay? And then we return the best D. So we have two penalizations for the number of coefficients and for the number for the size of the joint distribution. So the first step is I fix D, the joint distribution, and then I use the same procedure, okay? Now this is a multivariate expansion because this is multivariate distribution, but this is exactly the same thing. And we want to compare this density, this joint density, and this joint density. So we want to compare such a coefficient expansion. Okay, so we do the same thing. So this is for all k and for all d, but we fix d, we choose the k. Then after we choose the d, the best d. Okay. So that's what we do. This is just the generalization that the first thing that I showed just before. So this is exactly the same thing, but you have multivariate, multidimensional coefficients. So you have k. So this is an order. This is the total number of k, and then you have to put an order, okay? Before that was first coefficient, that was just n is equal to 1. Second coefficient is n is equal to 2. Now n or k is not k equal to 1, it doesn't mind something. So you have to look at the total order. Then you start with total order is equal to 1, but it could be 1, 0 or 0, 1. So you have different number of coefficients, okay? So you have just to put a lexicographic order, and that's all, and that's the same thing, okay? Okay, so this is K1, K2, okay. When you have an order equal to 2, you can have 1, 0, 1, 0, or 0, 1, 0, 1, or 2, 0, 2, 0, and so on. But the sum is equal to 2, okay. So you have, of course, much more coefficients to compare, but that's the same principle. Okay, so finally, you always consider a penalization. So you have your statistic, but now you have the number of coefficients in your statistic is the total number of k. Okay, so the penalization depends on the total number and of the combinatory of total number that you can have in your statistic. Okay, so that's exactly the same idea. Okay, and okay, so of course there are assumptions on the processes. Okay, you have something like the moments of the process and of the innovation, but this is technical assumptions. Okay, I do not show you, but the idea is that such penalization always tend to 1 if you are under the null. That is, if the processes are the same, all coefficients here, they are noise because they are equal. Okay, so asymptotically they tend to 0. So finally, if you put a penalization, the penalization is greater than the noise. So you just keep the first coefficient. And finally, so finally, you just choose the first difference. Okay, and now, which is the dimension that you want to compare? So it is exactly the same thing. Dn, it will be this is the number of coefficients. This is the dimension. Okay, this is 1 is just marginal. 2 is a bivariate density, and so on. And then you choose the best whole joint distribution with penalty. And the greater means that this is here you have difference. But again, if you are under the null, each time you have the same distribution. So the difference is only noise. And since you use again a penalization, then it will again be the first statistic that will be chosen. So finally, the notation is not very easy, but it's easy. Okay, you have 2 penalizations, k for the number of coefficients, and d for the dimension of the joint density. So you want to compare simultaneously which joint density is different or not, and which coefficients are different or not. And if there is no difference, then you keep the first, so that is just the marginal distribution and the first coefficient. And you have the same distribution than before, that is again a chi-square distribution. So that is a way to extend the marginal comparison to the whole distribution comparison. Okay, so now in conclusion, okay, but in the conclusion, the final statistic is asymptotically equal to this one, and that is just a comparison of the first coefficients. And you know that in this case, you have a chi-square distribution, and in application, you can compare alpha mixing processes, theta mixing processes, and transformation of linear processes. That's what we have done in our papers. Okay. What I want to show you now is just a numerical result. Okay. Just before an extension to the case of K processes. So this is Arfima processes, a pure functional model Arfima. So this is defined as follows. So theta is not necessarily an integer. Okay. So this is a generation of the Arima processes. And in the case where theta is in between 0 and half, this is a long-range dependence process. And what we do, we want to compare such processes. So the reference is this one, okay? So 0, 1, and this service. And then you propose another process, this one. If mu is 0 and sigma 2 is 1, mu is the mean of x, and sigma is the variance of the innovation of the epsilon in the process. If you have equality, you are under the null, of course, because you have equality of the two processes. And what we do, we change mu different to 0, or sigma different to 1, or more difficult, because it's easy to see that there is a difference in mean. That's easy to see it. Okay, but the first coefficient that can say it. It's also not too difficult to compare the difference of variance here. What is more difficult is when the dependence structure is very close, okay? Because it reflects dependence structure. When it is close to 0, it is close to the short range dependence. When it is close to 1, it is close to the case of it's close to the non-stationary case. Okay,
1/2.
1/2. Sorry, yes, you're right. Yes, so 0 it's close to the short, and 1/2 is a non-stationary case. Okay. And finally, here also the level results, you need more than 200 of 3 or maybe 400 observations to get a good level. Okay, so you need observations. The territory need to be greater than 200 or 300. You can see the power, but that's not very interesting. When I change the theta, you can detect if the parameters are not the same. What is interesting? I continue, okay, this is when you change mu or sigma. What is interesting is here, we choose 2 different arfima, but their margins are the same. They have Gaussian margin, okay, with exactly the same margin, but with different dependence. And here you can see that you can detect, except here, because when theta x is very close to theta y, it's difficult to detect the 2 processes. Okay, so that was the idea. Okay, and finally, this is 2 applications. One is for financial assets, so that with Dow Jones and New York Standard Exchange. What is interesting, just to say that it's very easy to apply, and you can compare the distribution. And the conclusion here is that you have a p-value equal to, you have a large p-value, so you do not reject the equality of the 2 processes here. And I show you another illustration. This is light curves that you can obtain. This is from the Kepler mission. So you go to the site of the NASA, and you can have many light curves. And then you can compare this both this one and this one, and okay, you can think that are not the same. And actually, no, the hypothesis is rejected, so this is not the same. And here, this is the same. Okay, there is no detection of difference here. Here, there is a detection of difference. Of course, this is very easy, but just to explain that you can. This is the result, okay? This is the p-value, so this is not equal, and this is p-value, so you can see that, okay, maybe it's equal. What it would be interesting to say, okay, I have many light curves, and I would like to make a clustering. It means that I have processes, and I want to know which have the same structure, and to have an automatic method. So that's what I want to show you now, okay? So this is not basically, this is very simple to understand because this is exactly the same theory that before, and I just use an adaptation. So what is the extension to the case sample case? For the moment, I just show you 2 processes, and I compare 2 processes. I want now to compare K processes. K processes. K means that this is the first process. This is the case process. Okay. And this is a joint distribution. I want to know if they have the same structure, so it's the same joint distribution. I want to construct a clustering method to regroup the same processes. So what we do, we use the method that that we have seen just before. I mean that we consider 2 processes, and we know how to compare 2 processes because this is a statistic that I presented. So, okay, TLM is a statistic that is able to compare the process L and the process M. Okay, I can do that because this is the same thing before. And what we do, we now again construct, this is again a new state, we again construct an embedded series of statistics. It means that the first will compare the first process and the second process. the second statistic, we compare. You remember that we try to increase the statistics, so we compare the first, the second, and the first and the third, okay? And so on. And this is the order. You can see this is an order like the elements of a matrix, okay? This is order 1, order 2 is this, 3 is this plus this one plus this one, and so on. And finally, you have the first statistic, that is, I compare the first process to the second. The second statistic is first, second, and first 3, and so on. And the last statistic, this is a finite number, because it's all the combinatorics that you can compute in your order. You have compared here all the processes 2 by 2. Why we do that? Because again, this is an embedded series, and then you can use the penalization. And that's what we do. So Vk contains k pairs of processes, and then we use such penalization. And again, we have the same result that says that if you are under the null, then since all processes are the same, all elements are noise, and due to the penalization, you just select the first one, and your statistic finally converges to the chi-square distribution. Oh, so how to use that to make a clustering of your processes? That's not difficult. You have, say, k processes. Okay. So I compute the difference 2 by 2. So I have to compute 2 by 2 among k processes. Okay. Then I first choose the lowest statistic. That is the 2 processes that are the closer. Okay. So I use the statistics, the minimal statistics, say process A and process B. It means that they are very close or not. But then I compare their distribution, the whole distribution at the test 2 by 2. Okay. If I do not reject this equality, I have the first group because they are the same. Okay. So you have, I show you. You have A, B, C, D. This is 4 processes. This one are the closest. The statistic is the minimal. The minimal statistic is T, A, D. Okay, this is the first statistic. I compare. If I accept, if H0 is true, okay. H0 is okay. Yes. If no, I stop because that was the minimal statistic. But all statistics are larger than this one. So there is no group. Sure. Okay, because these are very close, but these are not equal. So these are not equal. So there is no group. If I say yes, okay, this is yes, okay, this is my first group. AB, that's my first group. I continue, which is
C.
Close. This is C now. C is close to A or B. This is C. But now I introduce C and I ask, is A equal to B equal to C? If yes, I continue. If no, I stop. That was my first group. C is not equal, so C is now a candidate to another group, and I continue.
Yeah.
And check.
So I have a question.
Yes.
What does this mean? Is closed process?
In terms of statistics,
okay.
you have computed all the 2 by 2 statistics. This is 1, 2. This is an arbitrary order. Okay. So now I have computed T1, 2, T1, 3, T2, 3, T2.
Okay.
I choose the minimum.
Sorry, I have the same question in the public. So how do you choose the closest?
This is the closest statistic between all these statistics. The T, 2 by 2. You have a number of processes which are the closest in terms of statistics. You have computed T1, 2, T2. Okay, here you have.
I calculate everything.
You have computed T1, 2, T1, 3, T1, 4.
You should maybe write a little bit on the left, because here now I think the people on Zoom can maybe see, and that's a problem. Non mais putain, t'as un tableau là.
So, okay, this is an example. You have 4 processes. 1, 2, 3, 4. You have T1, T2, T1, 3, T1, 4. Okay. T2, 3, and T4, and T3, 4. Then you choose the minimum of such that is this one. Okay. So you compare is 1 is equal to 4. If yes, you continue. Which was close to 1 or 4? Maybe this one, or maybe this one. Not this one, because this is not related to this one. So I continue between this 1, 2, 3, 4 statistic, which is the closest to this one. Okay. Maybe this one. So I continue. Is 1 equal 4 equal 2? If yes, I continue. If no, I stop. This is my first group. Now I start with 2. Which is closest to 2? I try. No, these are not candidates because they are in a cluster. The only candidate now for 2 is 3. No, I just have to look to 3. Is equal or not? Yes, this is a new group. No, this is 2 separate groups.
Okay.
So if you do that, but you need the K-sample equality, because here I test 1 equal 4 equal 2. So if you need a K processes equality. This is not a 2 by 2 equality. So 2 by 2 is just to choose which is candidate. But the K is to say, okay, they are equal. And finally, this is just to conclude. This is illustration. So you have 2 groups. 2 are final with parameter 4.4. And 5 and 4 with parameter 0.1, okay? And we want to detect which are the same. So you use the clustering method. And of course, you want to say this group and this group. And so I made one, I don't remember what wasn't rent. And more than 50% case, you find the good group here, and here more than 70% case you find the good group. Okay, and sometimes this one is allowed because you think it is the same. Sometimes this 2 is also, but you can have a mix. But when the parameters are different, 0.4, 0.1, you can distinguish the group, and this is automatic. You have nothing to do. Just to choose the level of the test.
How do you choose the number of classes?
You do not choose the number of classes. You don't know. You don't know.
So always
sometimes when this is not the good group, sometimes he puts 3 groups, for instance. Okay. This one is wrong. These 4 are together. It can be that. Okay.
The logician, when it will finish.
Yes.
I don't know.
I choose this example.
Okay.
You have 9 processes. Okay. First, the algorithm it calculates all the 2 by 2 statistics. Okay, so you have 2 among 9. I don't know how much it is. He starts with the first 2 classes.
Yes.
Say this one. He said, okay, they are equal. This is the first group, but he doesn't know if they are again 1 group or 2 or 3. He continues. Maybe this one. This is equal. Okay, again 1 group. Maybe this one. Okay, this one. No. So a second group. This is wrong. This is wrong, but he said no. Okay. Then he continues with this one. Is equal to no. So this is alone. And then you continue here. This is equal. And you finish when you have tested all the. You have an order in the. You have an order. This one is closest. You start with the minimum statistic, and then you continue.
Okay. So
sure, when you have compared these 2 ones, if you say equal, they are in a group. That's finished. Okay. This is the first group. Okay. You can add this one if it's equal.
So it's very different from the clustering of neighborhood.
I think that's close to yes. That's a like of a neighborhood. K neighborhood. Yes, that's a kind of that's the same idea. Yes, But what is different that you have not like you have a lot of yes, you have not very center of the group.
Yeah.
This is a you have not a representative of the group.
Okay.
This is a group. You say yes or no. The group does not change. What it's changed, it's changed. But you had this one. Had this one. No. Okay. You do not change the very center comparison. So what I say, if I continue, Bajaya I finished. It's time, it's okay. If I continue with parameters very close now, 0.3 and 0.2, that's more difficult to distinguish. And finally, this is, you have many errors, but that's difficult to say, yes, that's a good group, okay? That's less difficult here because you have just 4. Because 5, you can, sometimes 1 is out, and so this is an error. So this is, you have more errors here because you have more processes in the group. I continue with the last case. This is, you have 4 same processes, 3 same processes, and 2 very extreme processes. This is very close to the short case, and this is very close to the non-stationary. Okay, and you can see that. Visually, but I don't know it. You can see that always it said that this one is alone, this one is alone, and sometimes there is missing here. Okay, this is mistake. Okay, that was the last slide. So in conclusion, it works well, except when the parameters are very close, and also.
What do you mean for very close? For instance, the difference.
I don't know. Yes, 0.2 and 0.3, that was close for me, but I don't know. Yes, you're right. 0.2 and 0.3, that was close. That was difficult to distinguish such processes. I don't know. I have not. I did not have time to compare such. But it needs time to say yes.
So you cannot discriminate at 0.4 against the 0.3.
No, I don't know. But no, for instance, that's just
basically you can distinguish between short memory and long memory.
Of course, yes. I think I did not try because I think it's easy because you see that when you have 0.0 and 0.49, it's sure that
it's non-stationarity
against
the short memory.
Yes, so that is you're sure. Yes.
In fact, many people use the fact that the trajectories are more regular when the exponent is bigger. And so that they use something like like the regularity of
maybe yes.
And that's because if you look between Arfima 0.2 and 0.3, already there is a 0.2 is a bit more like a group of things, and 0.3 is a bit.
I think
more...
you're right. I think we can see here. It's more clear here when you have points. You can see that the dependence structure is
more continuous function.
Yes, exactly.
More regular function.
Yes. And here this is very short memory. Yes.
That's exactly the point.
This is more easy here.
That's a Brownian motion against something like a deterministic process at the end.
It's a fraction by motion.
Yes, but when the exponent increases, you have very regular trajectories. The trajectory of regularities is calculated very easily. So people use that.
Yes.
But it is less general than your trick.
So finally, just to say that when parameters are close to the very, very large, close to 1/2, it's difficult to but it doesn't work very well. Okay. You can distinguish, of course, but if you have 2 processes with large memory parameters, but it doesn't work very, very well. Okay. Also, the multivariate case is very easy. It will be again a new step of expansion, but the problem, I think that the code will be more heavy to. And there is an extension to missing data that is in progress.
And did you think about random fields?
This is with Federico. I didn't talk about you. Okay. What?
Random fields? No.
it will be interesting also in this direction. I think that of course, this is a new, okay, this is a new dimension. Okay, so I think that we can, I'm sure that it works, yes. Because this is another penalization that you have to add in the parameter of time. Yes.
Okay. So I stop recording because else people will take all your IDs. Okay.
Sure.
So thank you very much.
Thank you.
Thank you.